In this video, we're going to talk about a couple different properties that graphs can have. And the first of these is the idea of a complete graph. So for instance, in K4, this is going to be the complete graph on 4 vertices that I've put up. We want to have one edge, exactly one edge, between every one of these vertices. And so it looks a little bit like this. Between the A and the B, there's an edge. Between the A and the C, there's an edge. Between the A and the D, there's an edge, and so on. So that's completeness. Next up, we have something called connected. Now, if I look at this particular graph here that I've put down, this ABCD, and I've got these 4 different edges, it has a property that if you're on any one vertex, say A, you want to get to any other one, like say the C, there is a way to do it. You could go and follow through the graph. It might not be a single edge, but there will be a path of multiple edges where you can get from any one vertex to any other. But what about this next one? In this one, I'm going to take the same base that I have here, and I'm going to overlay a EFGH1. So I've got the ABCD, and those have connections between them. I have this EFGH, and those have connections between them. But this is not connected because there is no way I can get from, say, A to E. There's no direct edge between A and E, and even if I follow some path where I go from vertex to vertex to vertex, if I start at A, I'm never getting to E. By the way, don't be confused. You see that the edges cross over, but the edges is just the way that I draw these. The idea of a graph is a bunch of vertices and then connections that tell you how to go from one vertex to another vertex to another vertex. So if I happen to have drawn them in the plane in some way where they look like they're crossing, I don't mean that you can actually go down and change at any of these crossing points. The rule is you have to go from vertex to vertex to vertex directly, and there's no way here to get from A to E, so not connected. By the way, in graph theory, what we often do with disconnected graphs is we say, well, look, actually, there's 2 different graphs. There's the ABCD, the EFGH. I'll study the ABCD one. Maybe some other time I'll go and study the EFGH one. But I just sort of treat them as 2 separate problems, even if I happen to overlay how I draw them on the screen here. Next up is the idea of a subgraph. So I'm going to begin with K4, the complete graph on 4 vertices. The idea of a subgraph is that you specify some subset of the vertices and some subset of the edges such that what you get is going to be a graph. So here I've highlighted I'm going to only focus on the A, the C, and the D, and I'm going to focus on 2 particular edges, the AD and the CD. And together, if I get rid of everything else, that's just going to make a graph. Now, notice that what you have has to become a graph. For example, if I'd left just the edge BD in there, but I didn't include the vertex, but I just had that edge, well, that wouldn't actually be a graph because the rule for a graph was that you had a bunch of vertices and all your edges went between 2 vertices. So that has to apply here to the idea of a subgraph. Final concept for this video is there's subgraphs, but there's also something called an induced subgraph. Notice how that we don't have a connection between A and C, but if you remember at the original, we did. The induced subgraph is like a subgraph, but it adds in every possible edge between the vertices that you've chosen for your subgraph. So in this case, if I've chosen the A, the C, and the D, I have to select every single edge that occurred in the original between the A and the C and the D. And so you get an induced subgraph. So the induced subgraph is sort of like the largest possible subgraph that comes from whatever vertices you've decided to retain. So now that we have this idea of connected and complete and subgraph and induced subgraph, we have a little bit of nomenclature of the basic ideas of graph theory.